technology is emerged as one of the most important and practically useful technology. So if you look at their applications, then it includes the wastewater treatment, food and beverages industries, pharmaceutical and biotechnology, chemical industries, and desalination. So since the application of the membrane technology is wide and vast, we would like to know first what is the membrane technology. So with that, I would like to give a simple definition of the membrane technology. Uh, Membrane is a semi-permeable material. So we can call it a semi-permeable material which can selectively pass certain species from one region to other region. So it can able to selectively pass certain species from one region to other region. Also, it can able to retain some of the solids on the surface of the membrane. So let us understand by going through this diagram. You can look at this figure. So the membrane is a semi-permeable material which can selectively pass certain species from one region to other region. So you can see here there are two regions. There are two regions. One is the feed region, another one is the permeate region. So there is the feed region, another one the permeate region. In between, some material is placed. That is called semi-permeable membrane. So it's a solid membrane. It's called semi-permeable material, which will allow certain solid or solvent to pass through and retain some of the solids over the surface of the membrane. So this is the concept. This how it's happening. This is happening due to various driving forces. So there are many driving forces are involving, such as concentration difference, pressure difference, temperature difference, and electromotive force difference. So such as differences, the driving forces are act on the membrane surface, but the true driving force is the delta V, which is the chemical potential, which cannot be measured directly, so that we are measuring the concentration difference, pressure difference, temperature difference, or electromotive force difference as a driving force for happening to pass certain species through the membrane and retain certain solids on the membrane surface. So broadly, two types of flow and filtration arrangements can be identified in the membrane separation process. One is the dead-end filtration, another one is the cross-flow filtration. So it can be understandable by look at the figure, the dead-end filtration arrangement. The feed is normal to the membrane surface. So the retained particles or the solids, you can call it as solids or particles, remain on the membrane surface and forming cake or gel layer. So the film directly to the membrane surface. So if you look at the cross-flow filtration, these arrangements the allows the fluid flows parallel to the membrane surface. So most of the particles or solids are retained or swept away with the flowing feed side of the liquid. So this is highly preferable since it gives a lesser fouling compared to the dead-end filtration arrangement. So this cross-flow arrangement involves less accumulation of solid particles on the membrane, and it is highly preferred in the industrial purposes. But both the cases, the separation occurs basically by the semi-exam. So if you talk about the type of membrane, there are several types of membrane can be available to us. So we can understand these types of membrane by taking up the example. So you can look at here. There is microfiltration, ultrafiltration, nanofiltration, and reverse osmosis membrane. So the membrane having the pore size in the range of 10 to 0.1 micrometer, that membrane is called as the microfiltration membrane. So it's a difference to the pore size. So the membrane is having the pore size range from 0.1 to 0.01 micrometer. That is called as the ultrafiltration membrane. For example, the microfiltration membrane can able to retain like suspended solids, oil emulsion, bacteria, cells, and colloid assay. These membranes, as I said, the pore size is ranging from 10 micron to 0.1 micrometer. For the next one, if you talk about the ultrafiltration membrane, which pore size is ranging from 0.1 to 0.01 micrometer, that can able to retain some viruses, macromolecules, and proteins can be separated by this ultrafiltration membrane. So, if you talk about lesser pore size membrane, for example, the pore size is ranging from 0.01 to 0.001 micrometer. That membranes are referred as the nanofiltration membrane. So, that can able to retain some of the submolecular organic groups and divalent ions can be retained by this nanofiltration membrane. So, the final one is the reverse osmosis membrane. The pore size ranging from 0.001 to 0.001 micrometer is usually called as the reverse osmosis membrane, that can even able to retain the monovalent ion, where the potable or drinking water purposes we are using this reverse osmosis membrane. So, and models, the membrane models is the way to incorporate it in the devices and the hardware to separate, feed into, permeate, and retain it. So the membrane processes, like we have the two region, one is the feed and the permeate region, where this also the models can be fabricated in the way separate the feed into, permeate, and retain it. So there are four models extensively utilized in the industries, such as flat sheet model, tubular model, hollow fiber model, and spiral wound model. So I have given here all four models, pictorial representations here. For example, circular or rectangle shaped membranes are resembled to filter paper. So this is kind of filter paper, the flat sheet model, where the shape can be round or rectangular or circular shape. So most general form of tubular membrane is bearing the resembles to single hollow tube of circular cross section. The wall can be working as a membrane in this case of tubular model. So feed can be sent to inner tube side as well as the outer tube side also. So the next one is the hollow fiber membrane model. This looks similar to the tubular form. It has a very small diameters uh, compared to the tubular model membrane. Typically, the fiber diameter is 1 micrometer in this case of hollow fiber model. So, in this spiral wound model, the two membrane sheets are diversified by mesh-like spacer with an active side facing away in the spiral wound membrane. So, these membrane edges of two membranes are glued in jointly with the fourth edge and open to the perforated center tube for permeation collections. So the other side can be enveloped the two mesh-like spacer positioned as feed path spacers. So finally the entire assemble will be rolled around the perforated center tube in a spiral configuration. So these all are the four models being utilized extensively, and these all are the basic about the membrane technology, where we can able to know that what is membrane process and the mode of operation and type of membrane and membrane models, available membrane models to us. So then I would like to talk about materials. So how the membranes are being prepared and what are the materials are being utilized for making the membranes. So membranes usually classified as a polymeric and ceramic membranes. The polymeric membranes are made up of polymers such as polysulfone, polyamide, polyether sulfone, polyacrylonitrile, and polypropylene, and any other polymer material can be utilized to make the polymeric membranes. So if you look at the ceramic membranes are made up of ceramic material such as alumina, zirconia, silica, titania, and kaolin, or some other ceramic materials also available to make the membrane. So the ceramic membranes have been developed over past few decades only, and now in the position to compete with the polymeric membrane, because that most of the membranes in practical use are in polymers. For the several decades, the most of the membranes are in practical use in polymers. Now the ceramic membrane have been developed over the for past few years and compete with the polymeric material. So it is because we can make the comparison between polymeric and ceramic membrane, where the polymeric or organic membranes are subject to mechanical damage, mechanical damage, and it can be chemically attacked. Uh, this polymeric membrane cannot be used in a harsh environmental condition for extreme pHs or in high temperature processes. And moreover, it having shorter lifetime and lowering the flux, and but there are some advantages with the polymeric membrane. One is the low capital cost, the polymer materials are cheap, and the simple manufacturing processes are involving in the polymeric membrane fabrication. But if you look at the ceramic membrane, it is superior mechanical strength, and it's very high compared to the polymeric membranes, and good chemical resistance compared to the polymeric membrane. And also, these ceramic membranes are having longer lifetime and also provide the higher flux compared to the polymeric membrane. But there are major drawbacks with ceramic membranes. One is the high capital cost. The ceramic materials are actually costly, and also it involves complex manufacturing process. So these two has to be addressed for making the ceramic membrane for commercialization and industrial usages. So if you look here that in the recent years, the potential utilization of ceramic membranes has greatly improved, especially in the broad range of industrial processes and pollution treatment technologies. So these ceramic membrane can be applied, as I said, in the extremely harsh environmental condition due to this distinct advantages. So most of the commercially available ceramic membranes are made up of with alumina, zirconia, titania, and the composite membranes. So also generally the ceramic membranes are made up of a composite formation with an active top layer. So you can look at this figure, this active top layer which typically decides the separation characteristics. So most of these active top layers are fabricated using inorganic oxides such as gamma alumina, jewelite, zirconia, titania, etc. So among these various axial materials, jewelite provide a well-defined pore structure and a better chemical thermal stability. Also, it exhibits excellent application in various separation processes, because what happens, this microfiltration membrane having some charge, so this charge membrane can facilitate to attain the good separation even utilizing the realistically larger pore sized membrane. So these are the advantage of using the composite membrane coated with axial materials such as jewelite, zirconia, titanium. And if you look at the industrial requirement, the tubular configured membranes are especially suitable in application where the feed stream contains the relatively high proportion of larger volume of feed particle, where the membrane exposed to extremely pH and the temperature condition. So, however, there is certain drawback for making this tubular configured ceramic membrane, because shaping by extrusion only achievable if the paste created from starting materials such as the raw material has rheological properties similar to those places. So making the ceramic tubular contribution membrane is quite difficult since the flake properties are very important. And this, as I said, the major drawback is the cost. The cost is mainly depends on raw material, sintering temperature, and method of fabrication. So this is all of the introductions for the material, and further information we have got what kind of configurations are required in the industrial process. So with that introduction, I would like to represent the literature on tubular ceramic membrane, where that findings tell us ceramic membrane research primarily addressed the fabrication of alpha alumina, which is the expensive raw material. Also, it requires a high sintering temperature. I have highlighted here, and it can provide the appropriate pore sizes, such as ranging from 0.1 to 1.2 micrometer, where we can use for microfiltration, or we can make a coating on the ceramic membrane to make the ultrafiltration or even the nanofiltration membrane. However, if you look at the sintering temperature, it's ranging from 1000 to 1600 degrees centigrade. So it's required a very high sintering temperature. So the major drawback of utilizing this aluminum material is the higher cost as well as the higher sintering temperature. So for this reason, researchers have started finding the alternative material such as corderite and apatite, Tunisian clay, natural clay, mullite, fly ash. So such a material they have alternative material they found and started making the membrane. And if you look at the sintering temperature, then also the sintering temperature are required 1200 degrees centigrade or above. So the sintering temperature also, some of the clays, the alternative material is high. Moreover, they couldn't get the appropriate pore size for suitable ultrafiltration or nanofiltration membrane. The pore size are just quite big. So from this literature study, so the ongoing research on the ceramic membranes are targeted to fabrication the membrane with the low cost material and lowering the sintering temperature at least less than 1000 degrees centigrade, and also finding the simple and cost effective technique, and also the pore size should be in the sub-micron range. It should not be a higher pore size. So also here I would like to represent the literature on Juliet ceramic composite membrane. So surprisingly, all the support material utilized for making the Juliet composite membrane are using as a alumina based material. So there are several Juliet, there are variety of Juliet researchers have studied and fabricated, but however they have used it as alumina as a support material. So which is costly, as I said. And moreover, the method of preparation, people have tried in situ hydrothermal treatment, which is a simple and widely used technique for making the composite membrane. So here the ongoing research for this Juliet composite membrane should target to utilization of low cost ceramic support instead of the alumina support, which is lesser the cost of fabrication cost of the ceramic composite membrane, and formation of various Juliet. So one can also find it out, for example, FAU or either ZSM or MFI. So such a Juliet material can be deposited on the support material to form the composite membranes by using this hydrothermal synthesis technique. So with that, so further, I would like to provide the major observation from the literatures. So most of the available ceramic membranes are alumina, silica, zirconia, and titanium. But these materials are now severely restricted due to their higher cost. You can look at the alumina material is $53 per kg. And also we identified that many of the researchers have used alpha alumina as a support material to fabricate the Juliet composite membrane. So the alpha alumina support material is approximately 500 US dollar per meter square. Also, it required greater than 1200 degree Celsius for membrane fabrication. So here, what we need to address in the ceramic membrane research, since its application is wide and vast, especially for wastewater treatment application. So, the preparation of ceramic membrane with low cost and excellent characteristics. So, we can make the membrane, as we seen in the literature, there are many membranes are prepared, but the characteristics such as pore size are sometimes bigger and the centering temperature is quite high. So it should have the excellent characteristics. That is a challenging task for upcoming development of the ceramic membrane. So here, one more thing we need to address, that is the reduction of sintering temperature. So we need to make the maximum reduction of sintering temperature at least below 1000 degrees Celsius. That will be beneficial for additional cost reduction of the membrane fabrication process, since the membrane fabrication process like expensive as compared to the polymer. It's more of the complex manufacturing process that has to be addressed in order to make the ceramic membrane feasibility to work in the industries. Also, there is a need to identify alternative low-cost material that can able to provide the support with excellent characteristics. So these are things we need to address. If you address, our expectation would be that as there is very little available literature on application of tubular ceramic membrane for industrial wastewater treatment. And developing countries like India, the successful penetration of this membrane technology into the industries has been thwarted due to the higher cost and the need of importing the membranes in bulk. So with that understanding, we have given the major thrust to give the minimization of membrane fabrication cost by using the low-cost clay materials available locally in India, and make the process commercially attractive. So with that understanding, we have framed some motivations to work towards the carry the further research on the ceramic membrane. So our motivations are as fabrication of ceramic membrane in tubular configuration, which is highly required for industrial purpose, and using locally available low-cost material by extrusion technique, which is a simple and cost-effective technique in order to make the tubular membrane formation. So after making the membrane will be characterized in detail, and we would like to test the membrane for two different wastewater. So we identified to test the membrane and oily wastewater and dairy wastewater treatment application by using the prepared membrane. Okay. Further, we would like to prepare the Juliet composite membrane. As we see, the Juliet composite membranes are prepared by using the alumina-based material, which is costly. Here, we would like to use the firstly prepared membrane as a support material for making the composite membrane. Also, we would like to test the performance evaluation of this prepared membrane. So, where we have developed two different Juliet types. One is FAU, that is phagicite, and the moderate framework inverted, the MFI Juliet membrane, the rigid resin category. So two different membranes we tried to make it, and also we have evaluated the potentiality in chromium removal. So these are all the motivation we have framed. So here you can see the fabrication of tubular ceramic membrane by extrusion technique. So we have identified the raw material such as ball clay, feldspar, iodine, ferroplate, quartz, and calcium carbonate. So these are the raw material we have procured from the vicinity of Kanpur, that is locally and abundantly available raw material. Because the choice of raw materials and the relative composition is very important to achieve the defect-free membrane material. So we were selected several locally available material as listed here as a raw material to fabricate low-cost membrane. And also we are objective, one of our objective was to contemplation of reducing the price of the membrane, and also we can assess our natural resource by using the local clay material. That is also one of the reasons to choose such a materials. So these raw materials are mineral grade and obtained in the vicinity of Kanpur. So these compositions are arrived, the optimal compositions are arrived by using the trial and error method. So the significance of this material I have provided here. The kaolin has a low plasticity and high refractory property, and ball clay provides plasticity and strength to the membrane. And feldspar act as to form glassy phase at lower temperature, and quartz increases the mechanical and thermal stability, and ferroplate reduces the fine cracks on the membrane surface, and calcium carbonate acting as a pore forming agent as well as the sintering agent. So these all are the material we have used, and the significance of having this material I have provided here, which is highly suitable for making the tubular shapeless ceramic membrane. So the pictures of fabricated membrane also I have provided here. So this tubular ceramic membrane was fabricated with a length 100 mm. So the composition, firstly, I would like to explain the membrane fabrication process. The composition of glaze here, such as ball clay, feldspar, kaolin, pyroplate, and quartz, taken for fabrication of the membrane as per the composition provided here, where the clay powder is accurately weighed for this purpose, and also we added some water, the requisite amount of water, in order to make a paste for the extrusion purpose. So this is the extruder we have designed and fabricated by using VP Ceramic Consultant located at Chennai. So for exclusively for making the tubular ceramic membrane. So in this case, we have not added any organic additives for the preparation of paste. We just added the water. So the obtained paste was fed into the extrusion cylinder here. So then the evacuation piston pushed the paste through a die in a tabletop extruder to form a tubular shaped ceramic membrane. So it is horizontally extruded, and we also conducted a certain velocity we have maintained in order to avoid the cracks while extruding. So when this extruding process reaching certain length, for example, this length is 100 mm, 10 centimeter, and 120 mm when it's reached, we to cut and or we stop the extruder process with the soft blades. We can also make the cut. So further, the prepared membrane, the extruder membrane was naturally dried for 12 hours, so in the atmospheric condition, and also further we dried at 100 degrees centigrade for 12 hours and 200 degrees centigrade for 12 hours, and finally we have, there are three different thermal processes we have carried out in order to avoid the sudden thermal shock and which create the cracks on the membrane surface. So further, the membrane was sintered at 950 degrees centigrade for 6 hours. So this sintering temperature also we have arrived by using various sintering temperature, the effect of sintering temperature we have studied, and chosen as the 950 degrees centigrade, which is less than lesser compared to the earlier studies what we have seen in the literatures. So the sintered membrane was polished and washed and also ultrasonicated in order to remove the loose particle sticker on the membrane surface. And finally, again, the membrane was dried at 100 degrees centigrade for further characterization. So you can see the different dimension of the membranes I have provided here, as that is the most important for the development of good quality membrane that should have the excellent surface, including the non-occurrence of any bigger pores or defects or cracks, and also it should have the good porosity, mechanical strength, and corrosion resistance. All are measured. We can discuss in the further slide. So this is the optimized procedure we have attained by going through the trial and error method. The perfect tubeless ceramic membranes was successfully prepared by following through this procedure. This obtained straight line, like straight with constant thickness. The constant thickness under this condition is a perfect condition we can able to obtain by making such a perfect membrane. And Further, the membrane we have characterized it by various analytical technique. So, like FECM images, you can see here, which these images we have used to analyze both the inner and outer surface morphology of the membrane, fabricated membrane. So, if you look at these membrane images, inner and outer images, provide the information on consistency of the prepared surfaces. So one can see here the homogeneous surface, also no cracks on the membrane surface able to uh, visible. So the membrane is highly smooth and flawless inner and outer surfaces we can able to achieve by following the procedure what we made it. So the overall surface morphology analysis recommends that non-appearance of cracks, defects, big pores is a key condition to lead the good quality of the membrane. So such a way the membrane has come up, and also we have measured the porosity of the membrane by using this expression, where porosity in percentage is equal to W wet minus W dry over rho water into volume of membrane 100, where W wet is the wet weight of the membrane, which measured by placing in distilled water for overnight, and W dry is the dry weight of the membrane, which was dried at 120 degrees centigrade for 3 hours. After that, we measured the dry weight, and the membrane volume, the total membrane volume was measured, and density of the water is uh, no. So the average porosity of the tubular membrane was calculated as 53 percentage, which is the prepared membrane is highly porous. Also, we measured the standard 3-point bending test we have performed to examine the mechanical strength of the membrane using this expression, where sigma is equal to 8 FL out over I into D out power 4 minus D in power 4. So where F is the applied force, L is the distance between the sample support points, that is in mm, that is in the tubular membrane, and D and D out are the inner and outer diameter of the tubular membrane, and sigma is the mechanical strength. So the average mechanical stability of the membrane was evaluated as 12 megapascal. This membrane is comparable. The values also we have compared with other membrane with alternative material. This is the mechanical strength is very high. For example, pyroplate membranes providing 5 megapascal mechanical strength. So also we have measured the chemical stability. This corrosion resistant tests were performed with respect to weight decrement of the membrane after keeping an ORS environment condition, such as acid and alkali. So the weight decrement of the membrane was estimated like 9% in acidic condition, and also 0% in alkali condition. So in acid and alkali conditions, the the prepared membrane was displayed the excellent result in resisting the corrosion. So most importantly, we have characterized the membrane. Also, we have fabricated the experimental setup, which will be useful for measuring the water flux as well as the conduction of separation or treatment applications. So I would like to explain the experimental setup here. For better understanding the schematic and pictorial representation of the prepared experimental setup I have provided here. Here you can see that this is the prepared membrane, and we also fabricated the tubular model, which is before fixing and after fixing. The pictures also I have provided here. So this system was formulated in a series of feed tank, metering pump for circulation of feed solution, and membrane model that is with tubular configuration, and pressure indicators and flow meters to measure the cross flow rate along with the control valves also available in the fabricated system. So the prepared tubular membrane was incorporated in the tubular tangential flow microfiltration setup, where the feed is to be pumped to the model from the feed tank and then applied with the recirculation mode. So with that experimental setup, we have measured the water flux of the membrane. So like water flux of the membrane. So, 5 different pressure we have utilized to measure the water flux of the membrane. Here, this figure it's represent the water flux of the membrane as a function of time for different applied pressures. So, a function of time and different applied pressure values represent as the steady flux we can able to attain for the entire measured time. So the stable and steady flux able to attain by using the prepared membrane. So this variation of applied pressure on water flux also represented here. So this is the respective time for each pressure and applied pressure water flux with respect to applied pressure. So it can be seen by this figure. The water flux increases linearly with the increase the applied pressure. This stipulates that variation in pressure is exclusively by the convection. So the flow rate is proportionate to the pressure, and it is also accordance with the Darcy's law. So with that linear behavior, the water permeability of the membrane was also determined by water flux at a different applied pressure. So it was evaluated from the slope of the pure water flux versus the applied pressure. The water permeability value is 5.93 into 10 to the power of 10 to the power of minus 7 meter cube per meter per second kilopascal. So after that, we can also able to measure the average pore size of the membrane by considering the pores of the membranes are cylindrical in shape, and this is the reduced form of Eigenvalue equation, which will allow us to find out the average pore diameter of the membrane. So it is R is equal to LH into 8 mu tau L over epsilon whole to the power of 1 by 2. So by using this expression, we have identified as the average pore size of the membrane is 0.309 micrometer, which is the microfiltration membrane. So the microfiltration membrane pore size is ranging from 0.1 to 1000 micrometer. Sorry, 10 micrometer. So in addition to that, we also calculated the manufacturing cost for prepared membrane. That manufacturing cost is can be calculated by at a laboratory level. We have made it which includes direct manufacturing cost and indirect manufacturing cost. The direct manufacturing cost includes raw materials, labor cost, electricity cost, and maintenance, laboratory cost. The indirect manufacturing cost include the capital cost of the for fabrication of this membrane. So we have followed, and we estimated that the manufacturing cost for making the one membrane is 0.5 US dollar, or it is 69 US dollar per meter square. So here the overall properties I have provided in the tabular form. These properties are highly comparable with the alumina-based ceramic membranes. So with these excellent properties, we would like to test this prepared membrane. So we have identified one of the wastewater treatment application, that is the oily wastewater treatment application. We would like to test this membrane as the pore size is microfiltration range, as the huge volume of oil wastewater was created from different process industries such as petrochemical, petroleum refineries, transportation, and metallurgical industries. So discharging of this effluent causes environmental pollution as well as decreases the yield of the oil. Therefore, the treatment of oily wastewater is compulsorily required before discharging in order to avoid the environmental pollution as well as the uh, decrement of yield of the oil. So, if you look at the some environmental regulations as per the Environmental Protection Rules, 1986, India, the Central Pollution Control Board, that is CPCB, framed the discharge limit of oil into surface water as 10 mg per liter, and public sewer, that is 20 mg per liter, and irrigator water it is 10 mg per liter, and coastal water it is 20 mg per liter from various industries. So for treating this oily wastewater, since it is generating from the several industries, there are several conventional techniques that have been used for oily wastewater treatment. So that include electrostatic collapse, treatment, filter collapse, and centrifugal settling, gravity settling, pH adjustment, and chemical emulsification. However, all these methods have some advantages and disadvantages. Sorry, and if you majorly, if you look at the drawbacks, these techniques, the conventional techniques are reasonably costly, and some technique also requires pre-treatments, and also many techniques provide the creating the huge sludge, and some technical heating treatment requires the higher energy, and some of the techniques also require the additional reagents, additional chemicals, that is also necessitates. And if you follow some of the technique, the conventional technique, there is some deficient in the removal of oil, because for example, wastewater containing the oily wastewater containing the higher concentration, the treatment is quite easy instead of treating the wastewater containing the lesser concentration. So in this case, the membrane performs very well. So with that idea, we also selected some lower concentration of oily wastewater for our study also. So also some processes are required longer operation period and imposes suspicious discard. So by considering these drawbacks, that membrane technology comes into sight as the best complete technology for treatment of oily wastewater among the various conventional techniques. In addition, it is very attractive due to the advantages such as compact design, lower energy requirement, and higher separation efficiency as compared to the other existing treatment processes which are conventional. So, however, the treatment cost also further lowered by choosing the microfiltration membranes, since they do not require the higher transmembrane pressure, and also it can able to provide the higher flux than ultrafiltration membrane. So our preferred membrane is the microfiltration membrane, which can be operated by at a lower pressure, applied pressure, and also it have the it can able to provide the higher flux. So with that motivation, we have applied for particular application called oily wastewater treatment uh, for our prepared locally available material place for making the membrane. That membrane we have tested. So here that oil droplet size distribution. So we have identified a different concentration range. All are kept a lower concentration. As I said, a higher concentration oil wastewater containing the higher concentration is easy with the conventional process. However, that lower concentration is very difficult. So we have made 50 ppm, 75 ppm, 100 ppm, 150 ppm, 200 ppm. The different concentration of oily wastewater we have prepared synthetically. So and analyzed for oil droplet distribution. This mean droplet size varies from 0.71 to 0.74 micrometer for 50, 75, and 100 ppm oil concentration, and 1.1 to 1.21 micrometer for 150 and 200 ppm oil concentration. That is, this oil droplet sizes are analyzed by using this laser particle size analyzer. So also we have decided to study that the three different parameter. One is the applied pressure and heat concentration. Applied pressure was ranging from 69 to 345 kilopascal, and feed concentration was ranging from 50 to 200 ppm, and the cross flow rates also we have varied. And observed rejection for this oil, we have estimated by using this expression provided here, where the CF is oil concentration in the feed stream and CP is the oil concentration in the permeate site, and R is the observed rejection. So also we have employed UV spectrophotometry for measuring the concentration of the oil, and it was measured at the wavelength of 236 nanometers. So each experimental condition, for example, applied pressure, we waited for 5 different applied pressure. For each experimental condition, the membrane was washed by passing the glistening agent, which is we have also the surf excel powder, that is 1 gram per liter, and the whole system cleaned by passing the millipore water for 1 hour. And after cleaning the process, the water flux of the membrane evaluated to show about negligible flux. So the full recuperation of the membrane inspected by calculating the membrane hydraulic permeability. So once the experiment at particular condition conducted, again we have regenerated the membrane. So the complete system was washed, and again the membrane permeability was measured, which is mean below plus or minus 2%. Then again we are going for the next experimental condition. So the performance of the prepared membrane in the synthetically prepared oily wastewater we have conducted. So the elaborated novel tubular ceramic membrane was applied for this purpose. So the applied pressure, feed oil concentration, and cross flow rates are the important variable in the treatment process that will affect the treatment process in terms of permeate flux and the rejection. So therefore, the effect of these parameters we have investigated as a function of time. So first we look at the applied pressure on permeate flux and rejection. So this figure is showing that the permeate flux profile with the time for various applied pressure, that is ranging from 69 kilopascal to 345 kilopascal. So here we fix the cross flow rate and field concentration is 100 ppm. So like in this figure we can observe that the permeate flux declines sharply at the initial period and become gradual thereafter in a microfiltration rate. So this the reason for this flux reductions are owing to the concentration polarization that will take place in the membrane surface, and also blocking of pores in porous ceramic structure. So this initial declinations of the flux can be the concentration polarization and also blacking of pores. So in addition to that, the permeate flux increases with the increasing this applied pressure. You can see here. This is due to the higher driving force that is acted on the membrane surface. However, the permeate flux profile on increasing the applied pressure does not follow the linear trend. You can see here, because if you water, we observe the linear trend, but in this case of oil wastewater, it is not a linear trend. This is due to the concentration polarization and adsorptive of oil on the surface that create the resistance to the transport liquid through the membrane. So this will be the reason for not obtaining the linear trend. And the rate of flux declination is higher at higher pressure. You can see here the flux declination is higher at higher pressure. That is due to the immediate formation of oil layer on the surface of the membrane. So what happens at the lower pressure, the rate of flux declination is less, and at higher pressure, the rate of flux declination is higher. So the higher pressure makes the membrane fouling the faster at a higher pressure. So this is the flux behavior's explanation. And on the other hand, if you look at the rejections, so this figure represents the rejection of oil with the time for various applied pressure. So it can be seen from this figure the oil rejections declines with increasing the applied pressure. So you can see here the oil rejection is declines with increasing the applied pressure. This is due to the fact that the higher pressure assists the enrichment of coalescence and the wetting of oil droplets. So therefore what happens, the imposing some oil droplet to transfer to the membrane force that attain the permeate side. So the higher pressure facilitates to enrich of coalescence and wetting of oil droplets, and imposing some of the oil droplet to transfer through the membrane pores and reach the permeate side. That is the reason. And the percentage of oil rejection is slightly increases with increasing the duration of the microfiltration run. So you can see here we have conducted the 1 hour study. So the percentage of oil rejection is increasing increasing with the microfiltration duration. This is due to the reduction of membrane pore size that will take place by absorption of oil droplets on the membrane surface, and the fabricated membrane exhibit excellent rejection performance by having the additional layer on the membrane surface. So the also we have studied the influence of feed concentration on permeate flux on the oil rejection. So this figure present the permeate flux plot with the time for various concentration. This figure clearly tells us the increase in oil concentration results higher flux declination. So you can see here the high applied pressure also flux declination is occurred. But if you look at the various feed concentration, it is clearly tell us the increase the oil concentration results the larger flux decline. Okay, the flux declination is happening with respect to the higher concentration, increasing the concentration. So the permeate flux is gradually decreases when the oil concentration is higher, where the oil sticks over the membrane and which creating the fouling, and also it resulting the declined permeate flux at higher feed concentration. So similar trend of flux behavior only reported in many of the literature due to the higher concentration in the feed side. So if you look at the rejection, on the other hand, if you look at the rejection, the influence of higher influence of concentration on permeate flux, as well as the rejection, if you look at it is enhances with increase in the feed concentration. So if you increase the feed concentration, the rejection is increasing. Why it is increasing? This is due to the enhancement of oil droplet size and the density of the droplet at higher concentration. So earlier we have conducted the oil droplet size of the oil droplet study, where the oil droplet size is increasing with increasing the concentration. So that increased the concentration with the oil droplet become size is become big, and it can retain on the membrane surface, which facilitating to have the higher rejection over here. So at this higher concentration, the coalescence of oil droplet form a larger droplet that will offer us the greater rejection. So also we have studied the cross flow rate, which is one of the important parameters. So that is also here represented permeate flux plots with respect to the time for different cross flow rate. So the permeate flux of membrane enhances with increasing the cross flow rate. This used to be the behavior. This can be understandable by like increment of cross flow rate reduces the concentration polarization. So what happens? The increasing the cross flow rate that will offer the enhancement in the shear stress on the membrane surface. So what that will do? That will eliminate the thickness of the sticked oil layer on the membrane surface. So the higher cross flow rate diminishes the thickness of the agreed oil layer on the membrane surface. So that signifies the uh, increasing the enhancing the permeate flux. So increasing the cross flow rate and enhancing the permeate flux. However, if you look at the rejections, so the oil rejection is slightly reduced with increasing the cross flow rate. That because of due to the reduction of oil layer thickness, because that oil layer thickness reducing by increasing the cross flow rate. So that is the so that is the reason. So however, if you look at lower cross flow rate, the formation of cake layer is more, and which act as the additional barrier on the surface of the membrane, which result in the improved oil rejection. So this higher cross flow rate depreciate the formation of cake layer. Accordingly, it reduces the rejection. The lower cross flow rate facilitate to have the higher rejection because of adherence of oil layer on the membrane surface. So further, we have evaluated the potential of the elaborated membrane with other membrane. So we have prepared the membrane. Also, we have applied for particular application. So that membrane performance has to be compared with the already available membrane or applied membrane for this particular wastewater. Since we have compared with the commercial available membrane also. So the performance of the present membranes in present treatment of oil wastewater application by using the literatures available literatures only. So it is evident from this table. You can see that that highest rejection. So what is the highest rejection we have obtained? That is 99.98 percentage, like at a lower pressure. So where we have applied this is 69 kilopascal only. If you compare this pressure, we have applied a 69 kilopascal. That is a lower pressure because we have prepared the microfiltration membrane that can be operated by lower pressure. Also, we have chosen that oil concentration is less oil concentration. As I said, the treatment of oil wastewater with a lower concentration is typical. So many of the conventional processes are not perform well when the oil concentration is low. So with that idea, we have chosen a lower concentration we have studied, and the cross flow rate you can see here, and permeate flux also we have a comparable permeate flux. And look at the projection, that is 99.98. So most of the studies and researchers also prefer using the alumina material, which performance and our prepared membrane performance is almost similar, and which give that we can replace the alumina membrane, which is costly. So such a way the prepared membrane, the Indian based membrane, the locally available material we have used here, that membrane is performed very well. So in addition to that, we also analyze the fouling study. Since the flux profile, the permeate flux profile, we have seen that there are flux declination in higher pressure as well as the higher concentration, and also we have obtained flux declination with respect to the cross flow rate, that role in the cross flow rate also. So we would like to study the fouling analysis for this particular application. So to identify the microfiltration flux profiles on the oily wastewater treatment application, we have studied 4 fouling models, such as complete, standard, intermediate, pore blocking, and cake filtration model. So all these models are analyzed. So I would like to explain these all 4 models. For better understanding, I have given here the pictorial representation of this model. So the complete pore blocking take place when the size of the solid particle is bigger than the pore size of the membrane. So it causes the pore blocking on surface of the membrane. Okay, so in this complete pore blocking model, this causes the pore blocking in the surface of the membrane and does not cause inside pores of the membrane. So you can see this figure; it's clearly understandable. So if you look at the standard pore blocking, so this standard pore blocking occurs due to the non-uniformity of the pore path. So there won't be any uniformity on the pore path, and when the solid particles are smaller than the pores of the membrane, it creates pore blocking inside the pores of the membrane. So it will create the pore blocking inside the pores of the membrane. Therefore, the pore volumes of a membrane decreases proportionately to the filtered volume of permeate in this standard pore blocking condition. So next one is the intermediate pore blocking that is to cause when the solid particle size and membrane pore size are not significantly block the pores of the membrane. So it may be blocked by some solid particle settling over another. So it is to be blocked by the solid particles settling over the another that will make non-blocked membrane surface area reduces with the time. So finally, the cake filtration model, which is applicable where the particle bigger than the average force of pore size accumulated on the surface of the membrane. So that will form the cake as it is represented here. So the cake will grow up with the time and it gives an extra porous barrier. So that's what happening in our study. That is the advantage of having this cake filtration model. So whether we need to test it, whether that model is occurred for our case, suitable for our case. So the cake used to grow up with time, as I said, and it also gives the extra barrier to permeating the liquid. So it will be forming as additional permeating layer on the membrane surface. So the porous extra porous barrier also impact the membrane separation characteristics. So these models by can be delineated with linearized equations. The equation I have not provided here, and I have that with the experimental data we have plotted these graphs. You can see here. So this cake filtration model. So we can the linearized plots of all the model I have presented over here: complete pore blocking model, standard pore blocking model, and intermediate pore blocking model, and cake filtration model. So the entire study that confirmed us that cake filtration model is the best fit with the obtained experimental results on wastewater treatment application on permeating profiles, the permeate flux profile. So these examinations throughout the microfiltration study or the associate to act the life of the membranes. Because what happens, the cake filtration is facilitating exterior fouling. So here you can see that the exterior fouling and may not provide a considerably towards the irreversible fouling of the membrane. So that will give us extended life of this membrane if the fouling causes in the filtration model. So, so that is all about treatment of oil wastewater treatment by using the fabricated membrane. And now we would like also discuss about the dairy wastewater treatment. This is another wastewater. That is a real industry wastewater we have conducted by using the prepared low-cost ceramic membrane, where the dairy industries are main and most important food industry in all over the world. And importantly, it requires a very large quantity of fresh water. Also, it generates large quantity of wastewater. For example, this dairy industry is generating 2.5 liter of wastewater for processing of 1 liter of milk. So that creates the it also requires the fresh water as well as generating the large quantity of wastewater. And mostly this dairy industry is not dealing with any high hazardous matter. However, the several contaminants are present, especially the organic matter, that is the chemical oxygen demand, that leads to cause issues and contaminate the environment. So this permissible limit as per the Central Pollution Control Board of India, the COD should be declined to 200 mg per liter to obtain the quality, that is the wastewater quality for discharge into the environment directly. So as we see in the oily wastewater treatment, there are several conventional techniques also available in the dairy wastewater treatment, such as physical, chemical, biological. Physical treatment requires includes sedimentation, screening, aeration, and chemical technique include chlorination, ozonation, coagulation, absorption, and ionizing. And the biological technique include aerobic and anaerobic methods. So these are the conventional processes, but the membrane technology is one of the emerging technology. So it performs well and economical also compared to the conventional technology. Since the conventional technology also identified as giving the poor COD removal, also many of the conventional technology also require higher cost for operation. Where we are utilizing the alternative technology as the membrane technology. So in this case, we would like to use our prepared membrane, which is indigenously prepared membrane for this particular application. Here also we have collected the dairy wastewater from real industry that is located in Purabi Dairy Wastewater, located in Guwahati, Assam. And the property of the wastewater is presented over here. Here we have studied the effect of pressure, the variation of pressure and cross flow rate we have studied, and rejection is observed by using the same formula what we followed for earlier case, and COD is measured by closed reflex spectrometric method. So the effect of applied pressure on permeate flux and COD removal. So you can see here that the figure is showing that the permeate flux profile with the time for various applied pressure. You can see here that various applied pressure we have studied, and the four different pressure we have studied. That figure we can understand that the permeate flux declines dramatically within a short period of time, and also became gradual thereafter during the microfiltration run. Okay, the similar flux behavior we can have for this particular wastewater treatment application also. The decrease in the flux can be explained concentration polarization on the membrane surface, also blocking the pores in the porous ceramic structure. So the concentration polarization membrane surface facilitated to have the flux decline, and another thing is you can notice that the permeate flux is increasing with the increasing pressure, and that is due to the higher driving force. However, the permeate flux does not follow the linear trend as in the earlier case, the entire operation. This is due to the concentration polarization, also absorption of the organic solids, which is highly presented in the dairy wastewater, and that will create the resistance to the transport of liquid through the membrane. So similarly, the rate of flux declination is higher at higher applied pressure. That is due to that sudden formation of organic layer on the membrane surface. That will make the membrane fouling faster in this case. So sorry, in the COD removal. So on the other hand, if you look at the COD removal, the similarly we have shown here COD with the time at different applied pressure. That COD removal is reduced with increasing this applied pressure. In this case, the influence of applied pressure. This is because of increase the COD content in the permeate stream side. That is due to the enhanced convective flux through the membrane due to the higher driving force at higher pressure. So the presence of large quantity organic matter retained on the membrane surface further facilitated to permeate through the membrane. So this organic matter presented on the membrane surface that is penetrating at higher pressure. So the higher pressure, that is the enhanced convective flux is taking place. That's why the organic content was deposited over the membrane surface is penetrating to the membrane and reaching the permeate site. That will increase the CO2 content on the permeate side. So, moreover, the percentage of CO2 removal increases with the microfiltration time. That is possibly to the development of cake layer resulting from the accumulation of particle on the membrane surface with the time. So, the as we know that that is formed cake layer acts as a secondary layer to produce the final filtration, which lead to increase the CO2 removal efficiency. So the cake layer also facilitated to increase the CO2 removal with respect to time. But if increasing the pressure, that is organic matter deposited on the membrane is penetrating through the membrane. So another case, the effect of cross flow rate on permeate flux and CO2 removal. So that is also presented over here. Similar way, it is can be observed from this figure. The permeate flux is enhancing with increasing the cross flow rate. So in this study, interestingly, the permeate flux is enhancing with increasing the cross flow rate. That is due to the reduction of concentration polarization on the membrane surface at the increased cross flow rate. So, like increasing this cross flow rate, like induces the shear stress on the membrane surface. So that will diminishing the thickness of the fouling layer on the membrane surface. So similar pattern is following for this particular wastewater treatment, and also reveals the increase in cross flow rate, decrease in the flux rate. That is possibly factor that the increasing cross flow restricts the cake layer formation on the membrane surface. So if you look at that percentage of CO2 removal, then the removal is reduced slightly with increasing the cross flow rate. This is due to the reduction of cake layer thickness on the membrane surface of the at the higher cross flow rate. So as we seen in the earlier discussion also, at a lower cross flow rate, the cake layer acts as the additional layer in the surface of the membrane. So the resulting friction is improved CO2 removal in this case. So this higher cross flow rate negatively impact the uh, formation of cake layer, and consecutively the removal is decreasing. So for this reason, the percentage of CO2 removal decreases with increasing the cross flow rate. So similar behavior also we obtained for this particular application. So we also analysis the fouling analysis by different pore blocking model, that is a complete pore blocking, standard pore blocking, and intermediate pore blocking and cake filtration model that confirmed that the cake filtration model is best fit for obtaining this experimental data. So for a prolonged lifetime, the cake filtration is the most important to facilitate the exterior fouling, thereby preventing the irreversible fouling of the membrane surface. So, according to the results obtained in this study, it can be most suitable, the best fit the cake filtration, that is for daily wastewater treatment, contribute the longer lifespan of the prepared membrane. So also we have made the potential evaluation with other membrane that is provided here. There are several membrane processes also carried out for dairy wastewater treatment. We have obtained a maximum of 91% COD removal, and the COD permit is 135 ml per liter. That meets the regulations framed by Central Pollution Control Board of India. Like CO2 removal in the daily wastewater using our prepared low-cost membrane is comparable over other membranes already reported in the literature. So, like the prepared membrane is better than that of other membranes in the CO2 removal from the industrial wastewater. You can see here, this is the collected wastewater from the real industry. And then after treatment with this prepared membrane, the water dish looks like this. So next is so we have prepared the membrane and applied for two different wastewater treatment, and both the wastewater can be directly discharged. One it is when it is treated with the preferred low cost ceramic membrane. So also we were talking about the composite membrane where the alumina utilized as a support material for making the composite membrane. So here we need to replace the alumina material and we would like to utilize the low cost membrane material what we have prepared. So with that idea we tried to make two different Juliet membrane. One is the fungicide Juliet membrane. Another one is the MFI Juliet membrane, that's modernate framework inverted Juliet membrane. For making this FAU Juliet membrane, that aluminate solution and silicate solutions are mixed and continuously stirred for 12 hours with this composition provided over here, and this solution mixture was transferred to the hydrothermal reactor where the prepared membrane material, this is used as a substrate, that is support material to make the Juliet membrane, kept inside the reactor. Then the reactor was tightly closed and conducted the hydrothermal treatment at 75 degrees Celsius for 12 hours. After that treatment, the membrane was recovered from the reactor and washed and dried at 100 degrees Celsius for further characterization and applications for chromium removal. Similar way, we have prepared the MFI Juliet membrane by using the hydrothermal treatment technique. That is the same technique we have followed, where the 2.8 gram of sodium hydroxide is added with the 200 ml of 1 molar of TPOH, a structural directing agent, and stirred for overnight, and 6.4 ml of liquid water we added in order to have this composition composition. So after preparation of this uh, reaction mixture, the reaction mixture was transferred to the autoclave reactor, where the tubular substrate was kept in the reactor, and the hydrothermal treatment was conducted at 185 degrees centigrade for 4 hours. So further after after conduction of this hydrothermal treatment, the membrane was recovered from the reactor and washed and dried and calcined at 400 degrees Celsius in order to remove the organic matter present in the membrane. So where here we have calcinized, but in this case we have not the calcination step is not required for FAH. So further the membrane was characterized and utilized for application. So we have also conducted some of the characterization study for the prepared membrane, the X-ray analysis of FAU Juliet, that high crystallinity and good agreement with the patterns of FAU Juliet. We can we will we can able to obtain by conducting the hydrothermal treatment technique, so that powder particles deposited on the reactor that was sticked over the membrane inside as well as outside. So on the bottom of the reactor we have collected the sample and conducted the study, and we are analyzed for XID. So the peak obtained at 2 theta value of 12.4 demonstrates the formation of high degree of crystallinity, and all peaks are consistent with the FAU report. So in the case of MFI, since the calcination step is required for MFI, so calcined as well as synthesis the powder we have listed for exciting. So high crystallinity and obtained profile is in good agreement with the pattern of MFI jewelite, and distinctive peaks obtained around 7.5 and 23.5 with other peaks, all are signifying the occurrence of pure base of jewelite, the type of jewelite MFI. So here you can see FESM analysis we have carried out for this is the inner and outer support. This figure we have seen very earlier also, that is smooth and flawless surface we have obtained. That is the support material. This is the support material. So you can see here after coating with the FAU jewelite, that is this is the FAU particles, and after coating with the FAU jewelite, you can see the surface of membrane, and after coating of MFI jewelite, like that is an interconnected particles are presented in MFI jewelate. So inner and outer surface. So for better understanding, I have provided inner and outer surface of the support and coated with the FA jewelate and also coated with the MFI jewelate. So this is the powder and I have shown here. And here the cross section view of the membrane. So this is the jewelate particle coated on the membrane, and this is the ceramic support. Similar case here also I have given the MFI jewelate surface and ceramic surface. So if you look at the observations, the synthesized jewelates are homogeneously dispersed in cubic unit structure of FAU, this case, and the interconnected pattern of MFI on the membrane surface. So you can see here, this is inner and outer surface on both sides, and a layer of jewelate microcrystal completely covers the ceramic substrate. So this is the ceramic substrate. You can see here in the inner and outer surface of ceramic substrate, the outer coating it completely covers. So the overall surface morphological analysis resembles that there is no cracks on the surface of the membrane. So there are no cracks, and the jewelate materials like FAU and MFI jewelate materials is distinctively visible in the FECM images. So all are provided neatly here. You can see here. So similarly, we have conducted the water flux measurement as we conducted for the substrate. So in all the cases, this is for ceramic support, this is for FAU membrane, this is for MFI membrane. So all the cases we can have like a stable and steady flux, we can able to have it. So if you look at the water flux, the function of applied pressure. So 5 different pressure we have measured. In all the cases, with respect to time, it is steady flux we can able to have, and the function of applied pressure, the flux is increasing with increasing the pressure. And however, if you look at that, this black line, the black line is represent the ceramic substrate, and the red line is represent the MFI membrane, and the blue also representing the FAU membrane. The flux is decreased compared to the ceramic substrate, the ceramic substrate without coating. So for here I have provided that in figure, like porosity of substrate, FAU membrane and MFI membrane. So the average pore size for support and 2 gel composite membrane, and the water permeability for substrate as well as the 2 composite membrane. So if I look at these values, porosity, average pore size, water permeability, so these values are decreasing with the, like both the composite membrane, these values are decreased from its substrate. So porosity, water permeability, and pore size of jewelate membranes are decreased. This is due to the incorporation of the jewelate layer on the ceramic substrate or support by the hydrothermal treatment. So this is due to the incorporation of jewelate material on the membrane surface. And if you look at the weight is increased. These are the values are decreased, and the weight is increased. Like for example, it is 8.7 gram to 9.9 gram for FAU membrane, and 8.7 gram to 9.95 gram for MFI membrane. So the weight is increased. This is also obviously due to the incorporation of jewelate layer on the membrane surface. So the water permeability of the ceramic support and the FAU and the MFI membranes are provided here. So these higher permeability values obtained is comparable to the other reported in the literature. So these water permeability values are comparable values others reported in the literature. So further, we have studied removal of chromium from aqueous solution using the jewelate membrane. As I said in the very early beginning of presentation, these composite membranes are not only separating the solid by pore size, even having the larger pore size, this charged membrane facilitate to obtain the rejection of solid because of electrostatic interaction between the membrane surface as well as the solid. So how it's happened, you can study with chromium removal, as that heavy metals are existence in the water, that is the major environmental concern that is increasing. The heavy metals such as lead, arsenic, chromium, cadmium, those are resistant in the water that will cause the health hazards. And if you look at the producing industries for these heavy metals, that is tanneries, metal plating facilities, paper industries, mining operation, fertilizers, and the pesticides industries, etc. So among these, the chromium is the widespread pollutant in surface water that can be available in trivalent and hexavalent oxidation states. So hexavalent is the highly toxic, that is 10 to 100 times than trivalent chromium. Also, it is very hard to eliminate from the water. So there is a carcinogen to human being and also causes a considerable hazard to the environment. So if you look at the regulations, the chromium in drinking water is 0.05 mg per liter as per the World Health Organization as well as the Central Pollution Control Board of India. So the similar experimental setup was used for this particular application also after making the Juliet composite membrane, where the separations were conducted at room temperature, the concentration were measured in conductive crystal, and the membrane cleaned with distilled water at higher pressure, and the water flux are determined to ensure there is no flux decline. So each experimental condition we have ensure that there is no every time the membrane was regenerated. So here also the various microfiltration studies we have conducted on feed pressure, feed concentration, and class flow rate. The observed rejection was evaluated by this expression what we discussed earlier. So influence of applied pressure on permeate flux and removal, the chromium removal. So this figure, so you can have that this is for FAU and this is for MFI. This is the flux profile and this is the removal, the percentage of removal profile. So the permeate fluxes with the time for both the Jurate membrane presented at various applied pressure. The fluxes, if you look at, are almost constant for the entire operation of the period. This is due to the insignificant contribution of absorption on membrane surface. So the chromium flux is marginally less than that of water flux of the membrane. So slightly less than that of water flux of the membrane. This is the typical behavior of a membrane process that is moving to generation of osmotic pressure by the retained ions. So that it leads to decrease in the effective pressure on the membrane surface. That is happening here. And if you look at the percentage of removal of chromium at a different applied pressure, for both the cases, the removal of chromium gradually augments with the filtration time, that is possibly to the development of concentration polarization until reach the steady state with the time on the surface of the membrane. The percentage chromium reveals increases with the increased applied pressure. Look at the percentage of chromium, it is increases with increasing the applied pressure. That is due to the formation of concentration polarization effect that not occur in the initial period of operation time. So at a higher applied pressure, it is happening. So also develop increasing the time it is retention of iron also within the process take place. So thereby the increasing the pressure, the convective transport become more significant than the diffusive transport. So that will make the percentage of chromium removal increasing with the increasing the pressure. That is due to the dilution effect, as the higher transport of solvent flux that it will result in a dilution of the permeation. Therefore, the higher permeation, higher applied pressure that will enable us to have the higher removal of chromium. So how it's happening, since that microfiltration, the pore size also bigger than the chromium ion. But as I said, it can be carried out by having some composite membrane such as Juliet composite membrane. So here I would like to, it is okay to point out that the surface of the membrane is the key factor of influencing the removal efficiency. Okay. So like when the membrane is dealing with the ionic solution, the surface charge is a very key factor here. So even if you have the pore size of the membrane is larger than the solid size, in this case what we have been saying. So the removal of solid by this that is the charged membrane, take place by electrostatic interaction between the charged membrane and the solids. Therefore, the surface charge of the membrane is depends on like as we know that the surface charge of the membrane is depends on the pH of the contact solution. That can be either positive or negative. So in this case, in order to find out the surface charge, we have carried out the zeta potential analysis at different pH, and um, here you can see here from it is clear from this figure, the electrostatic interaction played a very vital role on surface activity of FIU and the MFI tolate. So the electrostatic isoelectric point of both the tolate is found to be around 4. For example, FIU tolate it is 3.8 pH and MFI tolate is 4 pH. So both are good agreement with the isoelectric point value already reported in our study. So we have measured the isoelectric point. So since the isoelectric point of both the membranes, that is the period MFI membrane is 4, that's why what happened, the membrane is positively charged. The membrane is positively charged at pH less than 4, and the membrane is negatively charged when the pH of the solution is greater than 4. So when the charged membrane, that is this both the membrane is contacting with the chromic acid solution, the concentration of ions with the same charge. So talking about the concentration of the solution, ions with the same charge, like the membrane will lower near to the surface of the membrane. So that in the solution and the other ions, okay, which have the opposite charge. So the higher concentration, the membrane, what happens, the less than the solution contact solution of chromic acid solution is less than 4, it acts as a positively charged. At the same time, the membrane also acts as a positively charged. If it is more than 4 pH, it acts as a negatively charged membrane. So on the account of this concentration difference, the potential difference also generated at the interface between the membrane and the solution to the uh, and the solution. That will happen. That is due to maintenance of electrochemical equilibrium between the solution, that is the chromic acid solution, and the membrane. So sometimes we used to call as a donor potential also. So with this potential, what happened? The membrane is start repelling the ions with the same charge as the membrane. So for example, for this particular case, the aqueous solution, the chromium is usually present in a different form, such as HCrO4 minus, Cr2O7 2 minus, and CrO4 2 minus. So in this form, the chromium ions can be dissociated in the water. So particularly this study, the removal experiments are conducted at natural pH, that is around 2.35. That is the chromium available. The natural pH we have conducted. We have not altered the pH of the chromium solution. So the chromium return that majorly presents in the form of acid chromate ions. That is HCrO4 minus. So along with H3O plus in these experimental conditions, where the membrane also positively charged at this pH condition. So that's why the repulsion take place, that is positively charged membrane, and the positive species such as H3O plus will take place in this condition. So as the cation and anion cannot act anonymously, thereby that HCr O4 minus will also rejected to maintain the electroneutrality of the system. So such a way, the removal, the repulsion can take place and facilitating the removal even the membrane having the larger portions. So also we have studied the initial feed condition. So we have obtained a similar result for all the cases. The marginal flux decline we have obtained, that is due to the occurrence of incomplete plugging of membrane pores. And if you look at the removal is enhancing with the enhancing that is due to the different factors such as concentration, polarization, membrane folding, and osmotic pressure. So we also study the cross flow rate, where the increasing the cross flow rate contributes to increase the shear stress on the membrane, which is facilitated to have the enhanced cross flow rate, like a permeate flux on cross flow rate increment. And if you look at the removal, that is reducing with enhancing the cross flow rate, that is due to the thinner boundary layer on the membrane surface. So we have obtained a maximum of 82% of rejection for FAU membrane and 78% for MFI membrane. So that even though some of the membrane showed a higher percentage removal of chromium in comparison with the work what we have presented here. So the flux of the present study is 1 to 6 order higher than when compared to the other member. That is most important. The permeate flux is having the higher permeate flux is very important, where we can have the 1 to 6 order higher when compared to the other membrane reported in the literature. So also this membrane displays the reasonable removal percentage on the chromium removal applications. So with that, I would like to summarize the talk. So, to minimize the membrane fabrication cost and make the process commercially attractive, a prototype novel low-cost tubular membrane, that is one membrane is 0.5 US dollar and 69 US dollar per meter square, with excellent characteristics, was effectively fabricated by using the clay minerals materials available locally in India, such as Paul clay, pyroplate, and quartz. And the elaborated membrane is highly fulfilled in oily wastewater treatment by giving highest oil rejection, that is 99.98 percentage, and permeated water meets the specification given by Central Pollution Control Board of India for oily wastewater. Also, further, the fabricated membrane proved its application in dairy wastewater treatment, with achieving maximum reduction in COD up to 91 percentage. That is, we have brought down from around 2,500 mg per liter to 135 mg per liter, which is the permissible quality for discharge to the environment. And FAU and MFI type jewelry membranes were effectively fabricated on low-cost porous tubular ceramic substrate with good properties by hydrothermal synthesis technique. So further, we evaluated the potential of the prepared jewelry membrane, such as FAU jewelry membrane and MFI jewelry membrane, that were investigated by chromium removal and achieved the highest removal of 82% for FAU membrane and 78% for MFI membrane, with 1 to 6 order higher flux compared to the other membranes reported in the literature. And importantly, the FAU jewelry composite membrane is the best membrane as compared to the MFI membrane because of the certain advantages such as higher separation efficiency, requirement of lesser synthesis time, that is 24 hours, which within 24 hours you can make that membrane, and temperature is 75 degrees Celsius only. For a MFI membrane, it requires 185. Also, it does not require the calcination step in the FAU jewelry membrane. So with that, and these are some of our references of study. And with that, I conclude my talk and thank you very much. Hello. So, Joshua Daniel, he has asked what will it cost to prepare this membrane? Do we require special lab setup to prepare this? Dear Daniel, as we discussed in the today lecture, I'm audible to you. Hello, hello, Daniel. May I audible? Okay, thank you. So actually, we don't need to develop any extraordinary lab setup for making the membrane. For example, we need to have for making the circular shaped membrane or rectangular shaped membrane. So like a filter paper, the element will be like filter paper. We need to have the hydraulic pressing machine. So once the powder material can be kept in the mold, and the mold, the higher pressure, the membrane will be compacted. Further, that is after compaction, the membrane is to be called as a green membrane. Further, it will be allowed for thermal process uh, drying as well as the sintering. So for the sintering, after sintering, we can have the solid rigid membrane. So we need to have hydraulic press, and we need to have the basic important equipments I'm telling. We need to have hydraulic press, and for the drying purpose, we need to have that. Yeah, drying. We need to have it, and also for muffle furnace, we need to have for the sintering purpose. So these three equipments are required, and I have shown in the actually again I can show. So this is our lab. Actually, we are the new institution, as I said in my beginning of my talk, and just we have provided with some space. And as we have got some project, I have bought these equipments to make the membrane. So, for example, if you want to make this circular shaped membrane, like filter paper like membrane, you need to have this hydraulic pressing machine. So this pressing machine, so the material can be kept here with the mold, and the material can be compacted. So further, you need to have that hot air oven to dry it. Then also you need to have the muffle furnace. So the ultrasonicator also is to use for removal of unsticked, like a sticked particle on the membrane. So these are the major equipment for making this membrane. One, that hydraulic pressing machine, and hot air oven, muffle furnace. These are the three major equipment for making this circular shaped membrane. So this membrane can be kept here. That is a dead-end filtration. So the introduction of a membrane technology, I have explained what is the mode of operation. That is a dead-end filtration, where the feed will be perpendicular to the membrane surface, the normal to the membrane surface. So here we used to fix the membrane, and the pressure will be applied, and we can collect the permeate from here. So for making the membrane, you need to have the hydraulic press, hot air oven, muffle furnace, and for test the water flux, or if you want to do some kind of application, treatment of wastewater or separation of any liquid phase application, so you need to have it, this setup also. There is a dead filtration setup. If you want to make that tubular shaped membrane, so you need to have this extruder. This extruder machine we have designed and fabricated with the help of some industry, and where the material will be converted into the paste. In this case of hydraulic press machine, this dry pressing you can do it, but here you need to convert it into the paste. The paste, this is the cylinder where the die will be installed here, and the conical die, so through which the material will be passed, the tube will be extruded here. This is the extruded tube. So you need to, it will be like a little wet, and you need to keep it for natural drying, and you need to keep it for hot air oven. That purpose also you need to have that hot air oven. Further, you need to go for sintering. That is also the bumper furnace is required. So in order to evaluate the potentiality of this membrane, you need to fabricate a setup called tangential flow filtration setup for this tubular membrane. So you can see here, here we installed this tubular membrane, this prepared tubular membrane. So this is the entire setup available with us now. So we can able to make the membrane, and we can also able to test the membrane by using the dead end filtration for circular shaped membrane, and tangential flow filtration for the tubular membrane. So this is the, and the refrigerator maybe for application purpose we have it, and these are also very major equipment needed for the making the membrane. So like extraordinary lab setup may not be required for this purpose, as you are asking. Thank you, Daniel. I hope that I answered you.
Yeah, thank you,
No,
sir.
thank you.
Yeah, thank you for your insightful talk about that low-cost tubular ceramic membrane for wastewater treatment, sir.
Thank you very much.
So, participant, if you have any question, you can directly ask, sir, or you can message through chat box. I think, sir, no question from audience side.
Okay,
So,
okay.
thank you, sir. Thank you again.
Okay, thank you very much for inviting me and saying thank you. And also, if any of the participants, including the organizer, wants to make any collaboration with us, kindly contact me. And I can message my email ID on the chat box also. They can contact me, and we can work together.
Yeah, yes, sir.
So this is my email ID, and so this is my contact number. So participants also can contact me for any kind of collaboration. Thank you very much, all
Yeah,
of you.
thank you, sir.
Okay, may I leave? May I leave from the session?
Yeah, yeah, yes. No problem, sir.
Okay,
Thank you, sir. Thank
thank
you
you.
again, sir.
Bye,
Yeah.
bye to all the
Bye.
participants. Thank you.
Yeah. So, dear participant, so next session will start from start at I think 1:30. So please be there. So we'll meet again. Thank you.